This lesson is about finding function values. Remember, a function is something where we plug in an input and we get back one output. So that's what we're going to be doing. Values are what we call the specific outputs that we get when we plug in an input. So if we want to find the value of the function h of x when x equals 5, first it gives us this formula, h of x equals 2x minus 4, and it wants us to plug in the input of 5 to find out the value or output. We would plug in 5 for x, and then do the math on the right side, but ignore the left side. H of 5 is just a label telling us that we plugged 5 in to the function that was called h. The right side, 2 times 5 minus 4, is what we need to do our math. So 2 times 5 minus 4 is equal to 6, which means the value for the input when x equals 5 is 6. Or in other words, h of 5 equals 6. Now let's look at some graphs and tables. If we have a table and a graph, it's going to be a little bit different finding our values. On a graph, we merely need to look at the table and calculate when x equals a certain number, what our value or y number is. If we have a table where we're comparing the cost to the number of pounds that we're purchasing, and it does not start at 0, we would find our y-intercept by seeing what the value is when x equals 0. This can happen for different reasons. Let's say I want to buy pounds of potatoes, but I have to purchase first a container to put them in. In this case, when we buy 0 pounds, the cost is $4. That could mean that the container I bought to carry my potatoes in cost me $4. Then we're going to find the rate of change, which is how much it's going to go up for each pound of potatoes that we buy. This is also called the slope because we can use rise over run to find that rate. If my cost goes up $2 for every pound of potatoes that I buy, then our rate of change is $2 per pound. Let's look at a table. This table compares minutes to feet. For example, if I was watching a snail crawl across the ground, and every few minutes I checked how many feet away it was from the garbage can it was headed towards, I could keep track of that on a table. After 3 minutes, it was 14 feet away. After 7 minutes, it was 6 feet away, and so on. Since after 10 minutes it was 0 feet away, that means after 10 minutes it reached the garbage can. Let's find the y-intercept and the rate of change. We're going to find the rate of change first to see how fast this snail was going. Since the first change is 4 minutes and it went 8 feet, that means we would have -8 divided by 4. It's got 2 feet closer every minute that it was going. The same can be said when it goes from 7 minutes to 10 minutes. That was just 3 minutes that have gone by. And it went from 6 feet away to 0 feet away, which means it moved 6 feet, so that was -2. Now because we are comparing the feet away from something, the distance is going down or decreasing as it gets closer and closer to its target. So our snail is going 2 feet per minute, and so the distance that it's traveling is -2 feet per minute as it gets closer to that garbage can. We can use this rate to find our y-intercept. I only measured how far the snail was away after 3 minutes of standing there staring at it, but what if I had measured right at the beginning when the snail started moving? I could go back to time 0 and see what my y-intercept is. So, since we are measuring every few minutes, that is the independent variable, or x. And then the output is how many feet the snail has traveled closer to that garbage can, so that would be our output, or y. We're going to go back to 0 minutes and see how many feet away that snail started. Since it was 14 feet away after 3 minutes, we're going to subtract 3 minutes and go back to 0 minutes, or the very beginning. But since it's going 2 feet per minute, we have to take that 3 minutes and times it by our -2 feet per minute rate, and that will tell us that that snail started 20 feet away from the garbage can. So that's our y-intercept, 20 feet.